Um, Hello, everyone. Thank you for attending my talk. And unfortunately, I cannot be there, but today I'm going to talk about quadratic lower bounds on a stabilizer rank. This is a joint work with Said Mehraban, who was my previous supervisor, and you can find our paper on archive. In quantum complexity theory, we try to answer the main question that is there an efficient simulation of quantum computers on classical computers? And to this date, we have very strong evidence that the answer is probably negative because short factoring algorithm can factorize with very large numbers, but we don't have any classical algorithm that efficiently factors large numbers. And if there is some simulation, then you can simulate short factoring algorithms. So we believe that there shouldn't be a simulation. And in this talk, I'm trying to describe one specific simulation algorithm and understand the performance of that simulation algorithm. First, I reviewed what is a quantum algorithm in general. In abstract way, you have some classical function f, and on input x, you want to find f of x. And you first map your classical input x to some quantum state, and then apply some elementary unitaries. And at the end, you perform measurements, and the output of this measurement is supposed to be the output of your function f. And there is an important property that this U1 to UM, your elementary gates, they should belong to some gate set that has this feature of universality. This means that you can approximate any arbitrary quantum unitary with your gate set. And one particular example of universal gate set is this H, S, C naught, and T. And this is very simple set of matrices, and this would be important in the simulation algorithm that I will talk later. One very important theorem we have in quantum computing is this Gottesman-Neal theorem that says that if you have a quantum circuit consisting of only three gates, H, S, and C naught, then you can simulate it efficiently on a classical computer. And recall that we had 4 universal gates, and here we are excluding the T gate. And the proof is based on this stabilizer formalism. And in stabilizer formalism, we have 2 main ingredients, the Clifford circuits that are all the unitaries you can generate with H, S, and C naught. This is a subgroup of the unitary group. And the second ingredient is the stabilizer states, all the states that you can reach from if you start from all 0 and apply some Clifford circuit on the all 0 state. And there's some alternative definitions for both Clifford and stabilizer states. And for the stabilizer state, the alternative definition is this: is the set of states that are stabilized by a commutative subgroup of the Pauli group. And how this Gottesman-Neal algorithm works is it keeps efficient description of this commutative subgroup by keeping track of the generators of this subgroup, and it tries to update efficiently in each step. If you apply one of these Clifford gates, you can update the generators of that subgroup. This is not important for the purpose of this talk, but this is the main idea behind this Gottesman-Neal theorem. And we saw that we can do the quantum computing with 4 gates, and if you have only 3 gates, you can simulate it on a classical computer. And the question is whether you can somehow embed this 4th gate, the T gate, in your simulation algorithm. And there is one particular way of doing that, and that's based on using the idea of the gate teleportation. Here, if you have some arbitrary quantum circuit that is consisting of some Clifford gates and some number of T gates, there is a standard procedure that you can convert your circuit to some Clifford gates and measurements, and adding some ancillary qubits that are in some state called this ket T. And this T state is superposition of 0 and 1, and it's a balanced superposition, and it's somehow sometimes called the magic state. And you can see that this, you can check that these two circuits are completely equivalent. And then if you can somehow write this T to the K as linear combination of stabilizer state, then everything would be in this stabilizer formalism. And you can apply this Gottesman theorem to this arbitrary quantum circuit and simulate it on classical computers. So the only thing that should prevent us from not being able to simulate it on classical computer is that linear combination have a lot of terms, and we cannot do efficient simulation. I'm trying. I will try to make this idea more formal. We need to define this stabilizer rank. If you have some n-qubit quantum state phi, you can define the stabilizer rank as the minimum number of stabilizer states, such that you can write your state as a linear combination of that stabilizer states within some error delta. And this is some parameter that you can tune. And there is a terminology that we call it approximate rank if delta is greater than 0, and we call exact rank if delta is equal to 0. And the main result here is due to Bravi and Gossip, and it combines all these ideas and shows that if you have a quantum circuit consisting of n Clifford gates and KT gates, you can do big simulation with time complexity polynomial in n times the stabilizer rank, the approximate stabilizer rank of T to the K. And you can do the strong simulation in time complexity polynomial in n and this exact rank of T to the K. So this approximate and exact stabilizer rank of the magic state appears in the performance of this particular simulation algorithm, which is one of the most important simulation algorithm. And it's important to have some understanding of how it behaves with respect to this parameter K. If you believe that the quantum computers have more power than the classical computers, this shouldn't be a small number. This shouldn't be polynomial in K, but proving would be difficult. Now I'm going to review the previous results that exist on this stabilizer rank. In 2016, there was this lower bound square root n on the stabilizer rank of T to the n by Bravi, Smith, and Gossett. And then in 2021, there were 3 works that established very similar lower bounds. And stabilizer rank, for the exact rank, they proved linear lower bound, and for the approximate rank, they proved a square root n lower bound. And what we could prove was the approximate rank, and it also implies the exact rank, are at least quadratic. And this is the more precise version of our result, that it's at least n squared divided by some polylog factor times some constant that depends on this approximation parameter. And note that this is probably not optimal, but this is the best thing that we could prove so far. Before talking about the proof, I want to talk about some complexity theoretic implications of our result. In general, there is a context of representing some target function in terms of some simple functions. If you look at the set of all Boolean functions, we consider some subset and we call them simple functions, and we look at some target function G, and we try to characterize the complexity of this target function in terms of our simple functions. And the complexity is defined this way. We look at the minimum number of simple functions that you need, such that you can write the -1 to the power of your target function as the linear combination of these simple functions. It has the same flavor of the stabilizer rank, but in a different context. Now in in this framework, I look at two problems. The first problem is called a quadratic uncertainty conjecture. Here we choose the set of the simple functions to be the set of all quadratic polynomials over this field F2. And the target function would be the AND function. And the conjecture says that the number of terms in this definition should be at least exponential. And this is related to this stabilizer rank problem, because if you take some quadratic polynomial Q and form some quantum state in this way, these phases are determined by this quadratic polynomial, then this is a stabilizer state. And writing down some function in terms of this quadratic polynomial is very similar to writing down one state in terms of this stabilizer state. And the best lower bounds that people could prove was n/2. So there is a huge gap between what we believe is true, which is this exponential lower bound, and what we can prove, which is n/2. Another problem is if we take, again, the simple functions as the quadratic polynomials, and then Ryan Williams could prove that for any k greater than 1, there exists some function in NP such that you need at least n to the power k functions to write -1 to the power g as the linear combination of this function. And it was unknown before our result that whether there exists some function in P such that you need at least a linear number of terms. And with our result, we know that there exists some function in P that you need almost quadratic number of terms, and that this function is constructed based on the coefficients of this t to the n in computational basis. Now I'm sketching the proof. Before talking about the proof of our work, I want to talk about the proof of the previous work. All of the three works that establish linear lower bounds on the exact rank and square root n on the approximate rank, they had they were using different techniques, but they had almost a similar approach. They take some particular structure of this t to the n, and they showed that to capture that particular feature with a stabilizer state, you need at least linear number of terms. This was the main idea and approach, but they were using very clever and diverse ideas from linear algebra, higher order Fourier analysis, and number theory. But all of this approach stopped at proving a linear lower bound, and this is something that I called linear barrier, and we also have this linear barrier in that quadratic uncertainty conjecture. What we tried to do was a bit different. We said that, okay, proving lower bound and stabilizer rank of magic state is difficult, but what about a random state? And it turns out that we can prove very tight bound on the stabilizer rank of a random state. We can prove that the stabilizer rank of n-qubit random state is almost 2 to the n, and this is the maximum stabilizer rank that one state can have. And in the second step, we showed that if you have some random state, you can prepare that state using 2 to the n/2 T gates. And this is very crucial in our proof. And this is the main reason that we can go beyond that linear lower bounds. We can break that linear barrier. And in the second step, in the third step, we used that the idea of the gate teleportation to replace each T gate with Clifford and measurements and adding some ancilla in the magic state. And if you look at this picture, if you can somehow relate the stabilizer rank of this state to this 2 to the n, then we are almost done. We only need to do some change of variable to get the result. And that's exactly what we will do. I will go through each step in more details. The first step is proving lower bounds on the stabilizer rank of a random state. And for a random state, we prove that the stabilizer rank with overwhelming probability is at least 2 to the n over some polynomial in n. And the proof is not that complicated. We take some arbitrary stabilizer state S1 to SR, and we look at the span of this state. And we also look at the closest point to the random state in that subspace. And we can show that with very high probability, the norm of this vector, this closest point, is small. And this probability, we use some concentration inequality that is very sharp, and we can use union bound over all S1 to SR. And if you think about it, if you can show that that norm is small for large R, then it's equivalent to saying that the stabilizer rank is large. The second step is preparing some random state with T-gates. And if you just apply the Solovay-Kitaev, you can show that you can prepare some random state with 2 to the n Clifford and T-gates, but this is not enough for our result. We found a very interesting and non-trivial result that shows that in the first picture, you can trade some of the T-gates with Clifford gates. So you reduce the number of T-gates dramatically to 2 to the n over 2, but you might increase the number of Clifford gates, and we don't care about the number of Clifford gates in our proof. And in the last step, we take this circuit from the previous step, and we do the gate teleportation to replace each T-gate with Clifford and measurement, and we have some ancilla qubits that are in this magic state. And we could prove some lemma that the stabilizer rank of the output is less than the stabilizer rank of the input. And to prove that, it's important that this magic state is balanced. The probability of getting 0 and 1 when you measure T in computational basis are equal. And if you just write down what I told you in Word, you get this equation that the stabilizer rank of the input is larger than the stabilizer rank of the output, and the stabilizer rank of the output is 2 to the n due to the first step we had in the proof. And if you just do the change of variable n equal to 2 to the n over 2, you get the desired bound. Now I want to conclude with some possible future directions. The first and most obvious one is if we can go beyond the quadratic lower bound. And if we want to apply our approach, we need to analyze the T-gate complexity and stabilizer rank of some distribution. And for the Haar measure, we almost have the optimal quantities for these two measures. So you need to use more structured distributions to get something better than quadratic lower bound. And also, can we get some lower bounds that are based on some complexity assumptions? Because this stabilizer states, they appeared in simulation of quantum circuits. So it, with some complexity theoretic assumptions, you might prove some lower bounds. And the third direction is a robustness of a stabilizer rank, and how much the stabilizer rank depends on the approximation parameter. Right now, the best lower bound we have for exact and approximate are the same, and we believe that for exact rank, the lower bound should be more powerful. So can we improve the lower bound for exact rank using some robustness of the stabilizer rank? And finally, are there other kind of complexity theoretic implications of our result? For example, can we say something about this quadratic uncertainty principle conjecture or other questions in that area? I want to thank you for your attention, and I would be happy to answer any question you have.
Okay, thanks for the nice talk. So we have time for questions.
Hello. Could you give an intuition
Hi.
about this trading T gates for Clifford gates? Like, I think you didn't really say much about it. Is there any kind of intuition how that works?
That's a very good question. Actually, we were using some results from some papers. This is not our result that you can trading, but the main intuition is that if you have some oracle that do that query from some classical database, then you can prepare your state efficiently. And the main intuition is build that oracle with minimum number of T gates. And yeah, there is a paper in our references that that they have some smart ideas to build that oracle, but yeah, it's I don't have very high level intuition about that construction.
And might there be any way to like reduce T gates even more, or is there like a lower bound for that also?
If I'm not mistaken, in that paper, they prove that that's optimal. They cannot, but I'm not 100% sure, but I think that's the optimal thing.
Thank you.
Sure.
Yeah, I guess related to that, can you find other states where that have high rank but low T count? Is that viable strategy or?
That's a viable strategy. For example, if you have the deterministic distribution on only magical states, we believe that the stabilizer rank should be exponential, but the T-gate complexity is very small. It's linear. So that there are other distributions, but there should be some distribution that we can analyze the stabilizer rank. That's the main difficulty.
Yeah, go ahead.
Thanks. So I was wondering if you have m to be 2 to the n minus 1, so minus 1 not in the exponent, and you have what is your bound on a stabilized rank of t tensor m? Is it quadratic or linear?
So your n was so sorry, can you repeat the parameters? I was not sure I followed.
So you don't quite have 2 to the n tensor products, tensor factors, but only 2 to the n minus 1. And then I guess you can only do the lower one to the n half. Maybe I'm probably mistake something. You really get it for all states?
That 2 to the n minus 1, it wouldn't be important because yeah, it would be a factor 1/2. So we don't care about the constants. So as long as it's we have 2 to the n over 2, and that's n over 2 is important, the factor behind n. And we can somehow relate it to the stabilizer rank of the random state. Our proof works.
Thanks.
Sure.
Okay, we have time for maybe one more question. Okay, so let's thank the speaker and all the speakers of the session.